Welcome to the final lecture in Drawing Translation, Spring-Summer 2021. This is Drawing as Program, Algorithmic Logic in Image Making. This lecture is going to introduce you to concepts for the third module in the course, which has to do with the relationship between coding and drawing in order to produce a series of events or a sequence of actions, otherwise known as a program. So let's get started. What exactly is the meaning of program? This is a word that we encounter often in everyday life and society today, but do we actually know where it comes from or the breadth of what it means? So etymology is a word that means the root of a particular word or language, and so the etymology of program is actually quite old, dating back to the early 17th century, which, keep in mind, that means actually the century before the 1700s. So we're talking about early 1600s here, approximately 500 years ago. So the meaning of program comes from the sense of a written notice, an alert, or an announcement of some kind that would be printed matter, and it comes from Latin, late Latin, I should say, from Greek, from program or prographane, to write publicly. And so again, we have that sense that it's some kind of inscription, and it's meant to go out into the world. And if we break that down further, then pro in Greek signifies before, and graphene, to write. So this is a kind of pre-writing before we actually take it in as the finished product. And this concept will hopefully become clearer as we move along. So the meaning of program, its association today is obviously more with computers, but that's relatively recent in history, as I've just alluded to. And the common use of the word program describes, and this is across the past few centuries, just a series of events. So we could talk about a program as something, like an exercise program versus a computer program, or we could also talk about discussing the program of the evening. So if you were out at an event, whether it's a dinner or an award ceremony or a sports event, the program describes the series of what happens during the evening. Most importantly, we're concentrated on the sequence and the duration. These are the things that really define what kind of a program it is. And drawings, if we try to make a correlation here, which I certainly hope that you will, drawings also are, very much a sequence of actions that comprise an event, and they also have a specific duration. So there's a length to the drawing that it takes to complete it, and then also to take it in and perceive it. And finally, we arrive at a particular image or outcome, and so one must complete a program in order to complete a drawing. So here's the more mystifying term, which has a lot to do with programs, but also with drawing. What is an algorithm? In its simplest terms, an algorithm is a step-by-step approach to solving a given task. Doesn't matter whether it's happening digitally or analog, in the physical world or in the virtual world, we can still use the word algorithm to describe a step-by-step approach to solving a problem. And I would like you to think about and keep in mind throughout this third module that drawing is also a form of problem solving. And just because we're making a particular image, it doesn't mean that we're not addressing a challenge in completing that image. So the techniques that you use, the decisions that you make in order to finish that drawing and move from one mark to the next and one sort of area of the composition to the next is a form of problem solving. So the steps necessary to complete that drawing actually make an algorithm. Whether you record it or whether it's followed by somebody else at a later time, it actually doesn't really matter in terms of, just thinking about it as a concept and how these two things relate to one another. So each step that you take creates an algorithm in real time as you're completing your drawing. Algorithms are typically linear, But they're also, another characteristic that is linked to drawing is that they're often cyclical. So they will move in a circle and they will loop and come back to the beginning. And often when we draw, we need to reassess, once we've made a series of marks, whether the drawing is actually finished or whether a particular section looks the way that we want it to. And so when we circle back, perhaps literally or just conceptually in our minds, we're completing a loop and making a decision. And that's part of what an algorithm does as well. And so decision making also, we have options and we have clauses. And so often algorithms operate on these kinds of binaries. So we ask ourselves, is something true or false? Have we completed something? Yes or no? And then there are conditions as well. So if something occurred or if something didn't occur, else, meaning do something else in order to address it. One of the ways that algorithms relates really specifically to drawing is that algorithms have traditionally been visualized as flowcharts. You probably recognize this sort of visual language and aesthetic, but maybe you don't know it by the name flowchart, and that's okay. A flowchart is a diagrammatic representation of an algorithm, sometimes also referred to as a process map. And this is just a fancy way to say that it's a flowchart is a very quick and often minimal way to map how the algorithm moves through its various steps and stages. So if we look at this example on the left, we have a start and we have a finish, or the result, and we move through different steps in the sequence from A to B to C and to D. Notice that C is below D because C is actually part of a loop that brings us back around, whether to B or to the conclusion. So D is actually later in the sequence only if B proves to be true. If B proves to be false, then we move down to the bottom and we complete and we end the sequence. So while the algorithm is linear, it may appear to us nonlinear in a way because D actually is conditional upon C being true in the first place. Or I should say, it's conditional upon B being true, that we move through C and then to B and then back through D. Algorithms also, when they're visualized as flowcharts, represent a direct link between the practice of computer programming and creating algorithms in a digital context and communication design. So what I just did in terms of trying to parse this information, where after we start, we move to A and then down to B, and then there's a decision-making factor. So if it's false, we terminate, and if it's true, then we move to D and then down to C. This is a way of trying to get other people to understand that C and D are dependent on one another, and trying to make it as clear as possible in a visual sense. So the arrows provide us with a sense of direction and movement as we try to navigate from one node or one icon, one graphic representation to another. And really, these are abstract things that are taking place in a coding context. But even the sort of visual language here, where B is unique because it's a diamond and the others are rectangles, lets us know that it is different and that it is a condition in this case. And then orienting false and true close to these lines also, imbues them with meaning. So there is a kind of graphic design that's taking place. How successful it is or unsuccessful, I'm going to leave that up to you to digest and to come to a conclusion. But this is a little bridge to say that designing actions and operating systems on computers actually does require mapping this information out first and does involve communication design skills. So even though none of you are scientists, you're in design school, there is a interdisciplinary connection between these fields. Okay, let's look at a couple of examples of algorithms in a flowchart context, and we'll start with something that should be fairly familiar to you, which is performing a search. And this is in the Java context. Java is the most ubiquitous C-based programming language that builds most operating systems, whether you're on a Mac or Windows-based computer. So this should be how any search result is really functioning for you, whether you're performing it within the operating system or online. So this may seem inordinately complex at first, but it's really happening within a tenth of a second because of the speed of the algorithm. So I just want you to be aware that this complex process is taking place all the time, every time that you type something in to search for it. So our starting place up here is the empty search field. We type something in, we hit enter. After that, the computer is going to consider its entire input list, meaning all of the options, all of the search terms that are available to it. And then we have a conditional. It's going to compare what you typed in to the middle of that list. And this may seem a little odd, but computers, remember, function on binary language, zeros and ones. So everything that it does has to have either a yes or a no answer for it to advance. So the logical thing then is to divide the list in half, look at the exact middle term of that list, and then make a decision. If the search term is found, great. Output found, we move down to the result, and the search is over. However, most of the time, that's not going to be the case. So if the search term is not found as the exact middle of that list, then we move into another conditional, which says either if the term is less than the considered item, then yes, it moves down into the lower half of the input list. So if we think about the alphabet, we're thinking about letters M through Z. Otherwise, we move up into the upper half and search the top half of the alphabet. And then we go into another conditional state, and it parses this, sort of in a sequence of other halves, paring it down, looking at the middle of each of those sections of the list until we get a result. So is the considered list empty? No. We move back up. We do another conditional. If the search term is found, great, we found it, we get a result. And if the list is still empty after all of that, output is not found, and you get a result of blank, or result not found. So this tree is, again, performed at a fraction of a second, but it fuels basically everything that we do at this point in order to acquire knowledge, or for the convenience of just even searching what restaurant is still open around us. And this kind of algorithmic logic also can be moved easily into a drawing context. So let's look at that. Algorithm for drawing a tree. At the beginning, we're going to sit down to draw. This is where we start. We're going to select our paper and pencil or any other implement that you might use. The next step is to position and place that implement to the page. Then we begin to sketch our outline and basic structure of the tree. This probably includes the trunk and the largest branches. And then we actually need to move down into a conditional state after that. Is the structure accurate? So we're asking ourselves, have we completed what we wanted to, or have we, achieved the vision of this tree? Whether we're looking at it from observation or drawing it from our imagination, we have to ask ourselves this question either way before we can move on to the other details. So is the structure accurate according to us or according to what we're looking at? If the answer is no, we loop back and we go back to doing more of that outline and basic structure stage. If the answer is yes, then we can move on to adding leaves and surface details. After we add those, we again move down into a conditional state and ask ourselves, okay, now do we have enough of those? Do we have enough leaves and enough surface details? If the answer is no, then we add more and we keep looping back in this subsection of the algorithm until we satisfy the question. If the answer is yes, then we can move on to another conditional. Is there adequate value and volume? Basically, does the tree look three-dimensional? We move on to then another stage, if we pass that, which is to, if the answer is no, then we darken leaves and we add more shading. And if the answer is yes, then we can move on to thickening contours and adding a ground plane in order to, finish and polish that composition. Once again, this section of the algorithm can move in a loop. So until there is adequate value and volume, this becomes another kind of pocket or container area for the algorithm to circle and loop before it can continue to move on in the linear fashion. And then finally, we finish with our end result of a tree. I want to talk for a minute about how drawing actually occurs on screen and in the generation of computer graphics, because algorithms have been really important in bringing things to you now, like this presentation. And one of the key sort of inventions or discoveries was Bresenham's line. And this is going to look very rudimentary to you probably, but it forms a really important part of your everyday world, which is the generation of pixels in order to create images on an X and Y grid on a screen. So Bresenham's line is named after Jack Elton Bresenham, who developed it in 1962 while he was working at IBM, a famous software company that was instrumental in developing the personal computer. And what it does is that it maps a start point and an end point, and then the calculation gets the median average. It should just say the average distance between them in order to construct a straight line. And so based on the top left and the bottom right corner of where it passes through each of those available pixels on the screen, it fills them in. So this is why when we rasterize an image and we put it into pixels, otherwise known as a bitmap, a straight line is always sort of made out of these little steps. But it's because the vector, so that should sound familiar to you, the actual perfectly straight line from the start point to the end point needs to be converted into this square grid. So this is still in use today from basically every sort of piece of software that has a graphic user interface up to the most sophisticated that are used to draw, like Corel Draw or Photoshop. The same algorithm is still in use. And again, without this kind of sense of drawing through two-dimensional space in an algorithm, we wouldn't be able to create digital drawings that are more of a fine art or illustrative nature. So there is definitely a technical and also historical connection between these. Lastly, I just want to talk about and hopefully give you some inspiration by looking at some examples of contemporary artists who are thinking about algorithms and that, again, conceptual connection between computer programming and art making, and to hopefully inspire you for this next leg of the project. So one of those artists is Julie Meritou, who is an Ethiopian-born artist, but has lived and worked in the United States for many years, and she is world-renowned. She has shown at the Venice Biennale, she has work in all major museums around the globe, and her work was recently acquired by the AGO in Toronto. She actually starts using printmaking at some point in the last 10 years or so to inspire these drawings/paintings that she makes with ink and acrylic on canvas. And the wonderful thing about printmaking, especially intaglio, is that you make marks on a copper surface with an enamel emulsion, and then you submerge it in an acid bath. And you don't know exactly what's going to happen because it depends on the pressure of your mark into the enamel, how much it penetrates and allows the acid then to move down and penetrate into the metal. And then it also depends on the printing process. And from this, she started to create these sort of mechanical rhythms for her mark making and create series of marks that she would repeat over and over and over again, not always in the same place, but distributed around the canvas. And what she ended up creating were these series under the name of Invisible Sun that start to take on they're typographic, but they're also kind of geographic and architectural, and she had no real plan or outcome in mind. And this is where we step into the idea of generative art. And this can be a very powerful place to be in terms of using algorithms to your advantage, because she still had a method to the madness, quote unquote. She definitely had a precise sort of process in mind, but not a prescribed visual outcome. And that's actually what makes it very open, not only in terms of her experience in making it, but also open to interpretation. Next, this is a much older example. This is by Friederneck. This is Homage to Paul Klee, who is a French artist, or actually I should say a Swiss artist who worked mostly in Germany, and I'll talk about him in a second. But this piece was actually designed using a plotter, which is a mechanical device that draws on paper, and then output finally as a screen print, as a fine art piece, all the way back in 1965. So we're talking 70-ish years ago. And basically, it's all based on a simple mathematic formula that just gets repeated at different places on the page and in different scales and dimensions. And by doing this and altering the parameters slightly each time that he went back to plot it, he was able to create something that has pattern and structure, but also has a very enticing visual hierarchy to it, where we can tell that there are certain areas that are more dense and built up, and there are others that just appreciate the negative space. So it functions on both that fine art level and also on a kind of very technical programming level. And it was inspired mainly by Paul Klee's work, this piece in particular, Chateau et Soleil, also in English known as Castle and Sun. And you can see here, what's most significant about this is Paul Klee was an expressionist in the early 20th century, but mostly took inspiration from Cubism and Surrealism. And in Surrealism, there was this concept of automaticity, which means that you just do stuff and you kind of let your body guide the process. And it turns out however it turns out. And so while there is order and structure to this, you can also see a sense of spontaneity, and this is what Nack was trying to capture, even in the very precise process of putting it through a computer program. And then lastly, a more recent example, in 2014, John McCormick created an actual custom-coded algorithm that was based on biology, a biological concept called niche constructions, where organisms will often, actually the closest example is a beaver who builds a dam in order to alter the course of the river in order to build a better habitat for itself. And so this program that he created, the algorithm would draw a line until it intersected with another line, and then it would die, quote unquote, after that. But it would keep going in proximity to it and try to stay as close to that other line as possible. And it would create these beautiful, as you can see, organic sort of communities of lines together. And McCormick also used a plotter for this. And just to show you a little bit of what this looks like. So this is a machine that has a lever arm that moves back and forth and up and down. And it has different pens and pen widths associated with it. And so while the code is being input, it's live drawing onto the physical surface of the page. And normally it would be used to create these very, precise architectural renderings, but in this case, it was creating something very chaotic and organic. And so McCormick's idea here was to return us to that idea that program and algorithm are not always the kind of beautifully ordered, minimalistic visual space that we associate with them, but can also be very spontaneous and biological in their outputs. Okay, so a quick recap. Drawing is a step-by-step problem-solving process. Never forget that even though it is very quick sometimes and it can be very organic, that we are thinking through it second by second. And that algorithms relate to this because they advance in a linear progression and they loop back on themselves, much like one does when completing a drawing. Computer algorithms are often linear, so they move, through a sequence, but they also have direction and shape. They're not flat. So in that way that we create a drawing to have volume and dimension, algorithms also have this dimensionality. The parameters, the amount of options that we give to an algorithm or a drawing, determine the outcome. And so the more restricted our palette is, the more restrictive the outcome is, and vice versa. And then algorithms, finally, with open parameters, and this is something that you'll explore in your upcoming assignment, and what I mean by open parameters are ones where maybe even the user has the ability to change them or create input, lend themselves to this category of generative art, where we don't know exactly what we're going to end up with, but it all is derived from the base design of those parameters. So it's still a work of design and a work of art simultaneously. All right, well, thanks so much for your attention, and I hope that this has been helpful. I look forward to seeing what you create in this next module.